Dear students, আশা করি সবাই ভালো আছো. So today we are going to extend our discussions to what we have seen in our last class. In the last class, we have ended with Cauchy's integral theorem and some extensions to it. Today, today we are going to start with Cauchy's integral formula. এখন শুরু করার আগে তোমাদেরকে বলি যে আগে আমরা যেগুলো আলোচনা করেছিলাম স্পেশালি স্টার্টিং ফ্রম দ্য ডেফিনেশন অফ কমপ্লেক্স ফাংশনস টু Cauchy's ইন্টিগ্রাল থিওরেম, এই জায়গাটা খুব ভালো করে রিভাইজ করে নাও, বিকজ আদারওয়াইজ আজকের ডিসকাশনটা ডিফিকাল্ট হতে পারে বোঝার জন্য. সো উই স্টার্ট উইথ Cauchy's ইন্টিগ্রাল ফর্মুলা অ্যান্ড what does it say? It actually gives me the value of a function f in a region where it is analytic. So তোমরা বুঝতেই পারছো, it is a very important and strong formula in the field of complex analysis. It states that if f of z is analytic within and on a closed contour C, and if z equal to a is a point within C, I'm not saying that at z equal to a if f of a is not analytic. I'm just saying that z equal to a is a point inside the region bounded by a closed simple contour C, so that f of a, that means the value of f at z equal to a, is given by this formula, that 1 by 2 pi I closed integral over C f of z divided by z minus a dz, and this is called the Cauchy's integral formula. So how do I prove that? I have said that f of z is an analytic function within and on a closed contour C. So the integrand f of z divided by z minus a, if I call it to be g of z, then that is also analytic at all points within C, within and on C, except at z equal to a. এবারে আমি লাস্ট ক্লাসে যে এক্সারসাইজ তোমাদের দিয়েছিলাম একদম শেষে, যদি তোমরা সেটা কেউ করে থাকো তাহলে দিস প্রুফ উইল বিকাম ভেরি সিম্পল টু আন্ডারস্ট্যান্ড. What do I do? Let us just encircle the point z equal to a with a radius delta and denote that circle by gamma, say, and z equal to a is this point, and gamma traverses in the same direction as C. So within this region enclosed by C and gamma, g of z is analytic. If so, তাহলে আমরা as extension to Cauchy's integral theorem দেখেছিলাম যে this relation holds, that the integration over the closed contour C f of z by z minus a dz is the same as the integration over gamma f of z by z minus a dz, as g of z is analytic within the region bounded by C and gamma. So if gamma is the circle with its center at A and radius delta, then we can obviously write the equation for gamma as mod of z minus a equal to delta. So we can easily write z equal to a plus delta e to the power I theta. Now my variable becomes theta, where theta varies from 0 to 2 pi. So I extract dz from here. Then I perform the integration, that closed integral over C f of z over gamma f of z divided by z minus a dz equal to integration over 0 to 2 pi f of a plus delta e to the power I theta divided by delta e to the power I theta into I delta e to the power I theta d theta, and which immediately simplifies to this relation. Now this just choice of that circle, which is around the point z equal to a, that choice of that circle is in our hand, so that we can choose the circle to be infinitesimally small. That means we can choose delta to tend to 0. If so, then this integration over gamma, that is equal to integration closed integral over C, as we have seen in the last theorem. So integrate close integral over C f of z by z minus a dz in the left hand side, and in right hand side I put the limiting value of delta tending to 0 over this integration. And if since f of z is analytic, it is also continuous, so this relation boils down to simply I integration 0 to 2 pi f of a d theta when I make limit delta tending to 0. Alternatively, you can also think of it as, since the circle of radius delta tending to 0, therefore a point on the circumference almost coincides with its center, and f of z being continuous there, f of a is very close to f of a plus delta e to the power I theta. So immediately we get this quantity in the right hand side, and therefore f of a is 1 by 2 pi I close integral over c f of z by z minus a, sorry, the dz is missing here, and dz. So which immediately proves the Cauchy's integral formula. Now, as extensions to Cauchy's integral formula, we can also state these relations, and I am stating this here without proofs. This comes as the consequences of Cauchy's integral formula that if the pole of g of z is greater than of order 1, that is if the integrand is, say, f of z by z minus a whole square, then it is then f prime a, that means the first order derivative of f of z at z equal to a is given by this relation, and continuing likewise we get to the general one, that is f na, that is the nth order derivative of f at z equal to a is given by this relation, where n in general varies from, can take any values of 0, 1, 2, 3, etc. So as we always do, we'll perform some examples, but before that let me state another very important and strong relation in the field of complex analysis, that is given by Cauchy's inequality. What does it say? It actually gives us the modulus of the nth order derivative of a, which we have stated here. Cauchy's inequality gives an upper bound to this quantity as factorial n m by r to the power n, with some conditions, like if f of z is analytic within a circle C, that circle C is given by mod of z minus a equal to r, and if mod of z, f of z is less than equal to some number m on C, then this relation holds, and this is called the Cauchy's inequality. We can prove that very easily. Since we have to prove this relation, we start with fna, which is given by the previous theorem, previous formula for Cauchy's for the extension of Cauchy's integral formula. We start with that, and we take the modulus in both sides, in both the sides, so that we arrive at this relation. Right, up to this I think there is no difficulty to understand. So now, since z minus a equal to r, so we can write z minus a equal to r e to the power I theta. So that now my variable becomes theta in the polar form. So if I put this condition that f of mod of f of z is less than equal to m, so I get mod of fn a is less than equal to this quantity in the right hand side. Now here I have used that mod of I equal to 1, which is obvious, and mod of e to the power I n plus 1 theta equal to 1, which you can check using the Euler's formula. So I immediately get to this Cauchy's inequality, and hence that is proved. Now, as promised, we go to an example of Cauchy's integral formula. Say we have to evaluate this integration, where C is given by mod z equal to half. That is a circle at with center at 0 and with radius half. So I call it this integration to be I, and I just divide into two parts named as I1 and I2. Okay, so for I1, as we can easily see that the pole is at z equal to 0 of order 1, and for I2 the pole is at z equal to -1 with again order 1. Now what is the equation of the circle of the contour? That is mod z equal to half. So the point z equal to 0 is inside the circle, whereas the point z equal to -1 is outside the circle. So for I1 we have f of z equal to 1, because you remember we have called the integrand to be of the form of g of z, where g of z is equal to f of z divided by z minus z0. Here z0 equal to 0. So f of z here is 1, and f of 0 is equal to 1, which is quite easy to understand. So that integration over c dz by z equal to 2 pi I into f of 0 using Cauchy's integral formula directly, and which is equal to 2 pi I. And for I2, the pole is outside the contour, and henceforth by Cauchy's integral theorem, which we have studied in the last class, I2 thereby equal to 0. So I equal to I1 plus I2, which is nothing but 2 pi I. Likewise, I have given you two exercises, where the first one is very straightforward, and for the second one I have given a hint. You have to find the equation of the circle to know the center and the radius, then proceed in the same way as in the as shown in the example, because you need to know whether the pole is inside or outside the closed contour. Now, a residue is one very important property or very important part of the complex analysis. What do you understand about that word residue? Residue, what you understand is some leftover. আমাকে এক জুড়ি বল দেওয়া হয়েছে, তার মধ্যে থেকে খেলার উপযোগী কিছু বল যদি আমাকে বেছে নিতে হয়, তাহলে বাকি যেগুলো পড়ে থাকে সেগুলোকে আমরা রেসিডিউ বলি। সিমিলারলি এখানেও রেসিডিউ is something which will be left over, কিন্তু সেটা ইউজেবল নয় সেরকম নয়। That is the most important thing while evaluating some integration in the complex analysis. তাহলে প্রথমেই দেখি রেসিডিউ কাকে বলে এবং কেন বলে। আমরা এটা আগে আলোচনা করেছি যে if f of z is analytic in a region which is bounded by some closed contour C, say, except at a point z equal to z0, then we can enclose the point by, say, a circle of radius delta, and inside the annular region f of z is analytic then, and that can be expanded using the Lorentz theorem as f of z like this. What I have done, I have just taken out the part n equal to 1 over here and kept the rest of the part in terms of summation. Now what if we integrate f of z over the closed contour C? The first term directly vanishes in the limiting case of delta tending to 0 or z tending to z0 for all n. So this part goes away. What about this part? The third one, that also vanishes for all n. Remember, now the third part includes terms from n equal to 2 to infinity. This we have called the principal part, right? This we have called the principal part. So I have shown here the example with n equal to 2 only. For the rest of the terms, similar argument will be valid. So for n equal to 2, we are integrating b2 by z minus z0 whole square dz, closed integration over C, and I call it I1. So we have z minus z0 again equal to delta a to the power I theta, and thereby I extract dz. This is I1, and that is equal to b2 integration over 0 to 2 pi, and this is the integrand, right? So I just cancel out terms from numerator and denominator, and finally I boil down to this quantity, which is equal to 0 directly using the Euler's formula. You can check. So for n equal to 2, this term vanishes, and likewise for n equal to 3, 4, etc., all the terms vanishes. So what we have left with, this is 0, we are left with only this term now. What will be the result of the integration of this term? Say this is I equal to integration closed integral over c b1 by z minus z0 dz. Similarly, we again call z minus z0 equal to delta e to the power I theta, and I perform the integration in a similar manner, and what I arrived at is equal to 2 pi I into b1. So what I see that upon integration of a function f of z over a closed contour C bounding a region where f of z is analytic except at a point z equal to z0, then the only leftover is 2 pi I into b1, where b1 is the coefficient. What was b1? b1 is the coefficient of 1 by z minus z0 in the Laurent expansion of f of z, and thereby we call b1 the residue of f of z, at z equal to z0, right? Mathematically, we describe the residue of f of z for a simple pole at z equal to z0 by this quantity, limit z tending to z0, z minus z0 into f of z. Okay, there is an alternative method to express or to find the residue of f of z for a simple pole, that is pole of order 1 at z equal to z0. That might be useful at some cases, so let me just describe that to you. Say we express f of z in terms of two functions, the numerator f phi of z and the denominator psi of z, where psi of z equal to z minus z0 into capital F of z, with capital F at z equal to z0 is not equal to 0, which is obvious. We can define any function, we can express any function in the form of this, because any complex function in form of this, because the numerator will be some function which doesn't have a pole, and which the numerator has the numerator phi of z which doesn't have a pole, and the denominator which has a 0 at z equal to z0. So there will be a term containing z minus z0, and the rest I call capital F of z. So how do we find the residue at z equal to z0? As I have just defined, that it will be limit z tending to z0, z minus z0 into f of z, and putting this form of f of z over here, what I get is limit z tending to z0, z minus z0, phi of z by psi of z. Now, as I have said, phi of z and also psi of z does not have any singularity at z equal to z0. Only psi of z can have only psi of z has a 0 at z equal to z0. So I can expand phi of z and psi of z in terms of the Taylor series, so that we arrive at this expression. Now what is psi at z0? Psi at z0 equal to 0, because it has a term z minus z0 into it. So I put psi of z0 0 here and arrive at this expression. Now all the terms in the denominator has one factor z minus z0 in it. So that cancels with this z minus z0, and we are left with this expression, right? Now I put the limit z tending to z0, and directly all the terms vanishes in the numerator and the denominator except the first terms. So we are left with phi of z0, phi at z0 divided by psi prime at z0, which can also be used to find the residue of f of z at a simple pole z equal to z0, right? Now what if the pole is not simple? that is, it is a pole of, say, any order m. In that case, by definition, f of z can be expressed in terms of phi of z divided by z minus z0 whole to the power m. What I am done, given any function, it has something like z minus z0 whole to the power m in the denominator. So I kept that aside and call everything else as phi of z. Easy? Now, without going into the proof can again be done using the Laurent expansion and at the limiting case of z tending to z0. I am not going into the proof here. Just we need to remember that the residue for a pole of order m, small m, is given by anything, say m or r, whatever. I will call it r later in this lecture. So this can be called as m or r, and that is given by phi m minus 1 z0 divided by m minus 1 factorial, where phi m minus 1 z0 is the m minus 1th order derivative of phi of z evaluated at z equal to z0. Okay, this we have to keep in mind. So again, we will perform some example. First, let us find the residue of the function f of z equal to e to the power minus 1 by z at its polar singularity. This is one typical example where just by seeing, we can find the residue. How? Amra a to the power minus 1 by z ke sorashori expand korte pari in a form like this, and we have already said that the coefficient of the 1 by z term in the Laurent series, Laurent expansion, that will be my residue. So here the coefficient of 1 by z is minus 1. So that will be my residue for this function. Right? This is very simple. What if I give you this function? It is not so easy to express it, to expand it in Lorentz form. And we have to find the residues at all the singularities. It's not so difficult. We will apply our formulas that we have discussed. So the function is f of z equal to z by z minus 1 into z plus 1 whole square. This has poles of order 1 at z equal to 1 and pole of order 2 at z equal to minus 1. For z equal to 1, we'll call phi of z equal to z by z plus 1 whole square, because now f of z will be expressed like this, phi of z by z minus 1, as I have said. So f of z equal to phi of z by z minus 1, so that phi of z equal to z by z plus 1 whole square. As this is a pole of order m equal to 1, so we'll find the residue using this. Here there will be 0th order derivative, so that means only phi at z equal to z0, that means z equal to 1, so phi at 1 divided by factorial 0 m minus 1 factorial, that means 0 factorial, and directly we get 1/4. And for residues at z equal to minus 1, similarly we proceed, and since this is a pole of order 2, we'll have phi prime at z equal to minus 1 divided by m minus 1 factorial, that means 1 factorial, and we get the residue to be minus 1/4. There is one exercise for you to perform, and I've given the function. You find the residues at all its poles. Okay. Now, from here we arrive at the very strong theorem of complex analysis, namely the Cauchy's residue theorem. This we have already seen, right? This we have already seen under specific conditions, where b1 is the coefficient of 1 by z minus z0 in the Laurent expansion of f of z around z equal to z0, where z equal to z0 was a simple pole of f of z, and we have called b1 to be the residue of f of z at z equal to z0. Now, what if there are multiple poles? There is not one single pole at z equal to z0. So there are multiple poles at z equal to z1, z2, z3, etc. Cauchy's residue theorem gives us a generalization of this relation, that if there are multiple poles, And if f of z is analytic except at a finite number of poles within a closed boundary C and continuous on the boundary C, then closed integral over C f of z dz is given by 2 pi r I summation over r, where r summation over r is sum over all the residues. That is r, say r1 is the residue at z equal to 1, r2 is the residue at z equal to z2, where z1, z2 are the poles. Then the evaluation of this integral, the result of this integration will be simply 2 pi I times sum over all the residues. That is r1 plus r2 plus r3, etc. Clear? However, one thing to be kept in mind is that while performing this right hand side, we have to consider only those poles which lies within this C. That means the residues at the poles which are outside C will not be considered while evaluating this integration. That we have to keep in mind. Again, let me show you an example that will clear the confusion if there is any. Determine the poles of the following function and residues at each pole. The function is given by f of z equal to 4 minus 3z divided by z into z minus 1 into z minus 2. And hence evaluate this integration, where C is given by mod z equal to 3 by 2. Okay. How do we perform? See, the poles of f of z are at z equal to 0, 1 and 2. That is clear looking at the function. So I have already shown how to find the residue. We find the residue at z equal to 0, at z equal to 1 and at z equal to 2. Now what is the closed contour? The closed contour is mod z equal to 3 by 2. So only the poles at z equal to 0 and z equal to 1 will be contained within that contour C, and at z equal to 2, that pole will be outside the contour C. So according to Cauchy's residue theorem, z equal to 2 should not be considered, and hence closed integral over C f of z, this is closed integral over C f of z dz equal to 2 pi I times the residue at z equal to 0 and plus the residue at z equal to 1, which is simply 2 pi I. This is why we apply the Cauchy's residue theorem while evaluating an integration over a closed contour C. I give you an exercise to perform, which is very simple, and you can perform, I hope, directly. If in case of any problem, if you face any problem, let me know. I'll try to explain that to you. So here we pause for this lecture. Next day we'll carry on and we'll see some more interesting facts about complex analysis. Thank you.